Physicists and cosmologists have long held that the universe originated approximately 13.7 billion years ago through a colossal event known as the Big Bang. This theory posits that all matter, energy, space, and even time itself began at a single point of infinite density and temperature referred to as a singularity. At this critical moment, the entire fabric of the cosmos exploded outward in an almost inconceivable release of energy, setting the universe into a state of rapid expansion that continues to this day. Over time, the Big Bang theory has become the most widely accepted scientific explanation for the origin and development of the cosmos. But despite its foundational status in modern cosmology, there are still many unanswered questions. Chief among them is, what caused this explosive event to occur in the first place, and what came before it, if anything? To address such profound questions, scientists have invested decades of effort into studying the physical laws that govern the universe. Through meticulous observations, theoretical models, and advanced simulations, researchers have built a framework that explains a wide range of phenomena, from the formation of atoms and galaxies to the cosmic microwave background radiation. Central to this framework is the notion of dark energy, an unseen force that is believed to be responsible for the accelerated expansion of the universe. Unlike normal matter, dark energy doesn't clump together or emit light. Instead, it acts as a sort of anti-gravitational field that drives galaxies apart over vast cosmic distances. It is estimated that dark energy constitutes about 68% of the universe's total energy content, making it a dominant factor in its evolution. However, our understanding of the cosmos is far from complete. Scientific models must constantly adapt in light of new data, and recent observations from the James Webb Space Telescope, JWST, are challenging some of the core tenets of the Big Bang theory. This powerful new telescope, launched by NASA in partnership with the European and Canadian space agencies, was designed to peer farther into space and thus further back in time than any of its predecessors. Equipped with state-of-the-art infrared imaging capabilities, the JWST has already begun to deliver data that defy conventional expectations. Among its most startling discoveries are over 750 previously undetected galaxies, many of which appear radically different from what cosmologists had predicted. These galaxies are not only far more numerous than expected, but they also exhibit characteristics that make them difficult to reconcile with the Big Bang framework. For instance, many of these galaxies are surprisingly compact, smooth, and ancient. Some of them possess mature, well-formed structures such as spiral arms and disk-like configurations, features typically associated with galaxies that have undergone billions of years of evolution. The implication is that these galaxies must have formed incredibly quickly, possibly within a few 100 million years after the supposed Big Bang, which contradicts established models that suggest galaxy formation is a slow and chaotic process. This has caused considerable debate and concern within the scientific community. In fact, some researchers have described the situation as a cosmological crisis, indicating that the standard model of cosmology may need serious revision. There are even articles and headlines that include words like panic, signaling just how unexpected and disruptive these findings are. The galaxies captured by JWST seem too small, too smooth, too old, and too plentiful to fit comfortably within the existing timeline of cosmic evolution as laid out by the Big Bang theory. If these observations are verified, they may force scientists to fundamentally reconsider how the universe began and evolved. To appreciate the significance of these discoveries, it helps to understand how the Big Bang theory describes the early universe. According to this model, all matter and energy were initially compressed into a single point, a singularity, where conventional laws of physics break down. From this state of infinite density and temperature, the universe underwent a rapid period of inflation. In a fraction of a second, space itself expanded faster than the speed of light, stretching quantum fluctuations into the seeds of galaxies and cosmic structure. After inflation ended, the universe continued to expand at a slower but steady pace. During the first few minutes, a process called nucleosynthesis produced the lightest elements, such as hydrogen, helium, and trace amounts of lithium. Over millions of years, gravity caused gas clouds to collapse and form stars, which then grouped together to create galaxies. The JWST findings disrupt this narrative in several key ways. First, the telescope shows galaxies that should not yet exist at such an early epoch in the universe's history. According to the standard timeline, there simply wouldn't have been enough time for gas clouds to condense, stars to ignite, and structured galaxies to emerge with such symmetry and stability. Second, the galaxies appear far too smooth and well-organized. If the early universe was as chaotic and collision-filled as theorized, we would expect to see more irregular, disrupted galaxies. Instead, JWST reveals galaxies that resemble the elegant spirals and disks seen in our local universe today. Additionally, the scale and perspective effects predicted by the expanding universe model, such as objects appearing smaller and dimmer with increasing distance, are not fully aligning with what JWST has detected. Some of the galaxies observed appear 2 to 3 times smaller than similar ones imaged by the Hubble Space Telescope, which is inconsistent with what we would expect if the universe had been expanding uniformly from a singular point. These inconsistencies are forcing researchers to revisit not only the timing of galaxy formation, but also the very mechanisms that might be responsible for shaping the universe. Another critical finding involves the analysis of light from these distant galaxies. The JWST's infrared sensors allow astronomers to study the color and composition of ancient starlight. By examining the light spectrum, scientists can estimate the age of stars and infer the developmental stage of galaxies. Many of the galaxies JWST has observed contain older stellar populations than expected, further challenging the notion that these systems only recently came into being. Some theorists, such as physicist Michio Kaku, have speculated that these findings could mark the beginning of a major paradigm shift in cosmology. If the Big Bang cannot fully account for the age, structure, and distribution of galaxies, we may be on the verge of developing new theories that better explain the cosmos. These might include revisions to general relativity, alternative models of cosmic inflation, or entirely new frameworks such as cyclic universes or quantum gravity theories. Whatever the eventual outcome, it is clear that our understanding of the universe is undergoing a profound transformation. In conclusion, while the Big Bang theory has served as a powerful tool for explaining the origins of the cosmos, the recent data from the James Webb Space Telescope suggests that our cosmic history may be far more complex than we once believed. These observations not only deepen our sense of wonder, but also remind us that science is an ever-evolving pursuit. As we continue to explore the farthest reaches of space, we may find that the story of the universe's birth and evolution is still being written. If you enjoyed this exploration of cosmic discovery, don't forget to like the video, share it with others who are curious about the universe, and subscribe to our channel to stay updated on the latest revelations from deep space. Together, let's journey further into the unknown and uncover the mysteries of the cosmos.